Hello, my name is Juwan Rowe, and I am a junior at Auburn High School. Today, I would like to discuss with you my project on the identification of lipid positional isomers using epoxidation and periodate oxidation with mass spectrometry for improved detection of bacteria. As many may already know, various methods to detect bacteria already exist, including PCR. But these methods often require expensive equipment and material and are also time-consuming. The goal of my project is to develop a new method for bacteria detection that uses minimal resources and takes less time. Lipids are the main components of cell membrane, which exist in all organisms. Bacteria are no exception and thus have different types of lipids in their plasma membrane. Each type of bacteria have different types of lipids, which may vary both by mass and structure. Paper spray mass spectrometry can be used to quickly distinguish between the lipids of different masses, where the user would simply add the analyte onto a piece of paper and allow it to be taken in by the mass spectrometer. The mass spectrometer then analyzes the particles and determines their mass. A problem with this method, however, is that it cannot distinguish between isomers, notably the position of the double bonds. This especially becomes a problem at the subspecies level, where the MZ data becomes difficult to distinguish. To solve this, a series of reactions were used to break the double bonds on the fatty acid tails, which would give off a certain mass that can be evaluated to figure out the identity of. The first reaction used was epoxidation, which is where a peroxy acid reacts with an alkene, which is the double bond on the fatty acid tail in this case, to form epoxide rings. When analyzed through the mass spectrometer, the data would show an increase of 16 for each double bond since oxygen is added. The next step was the acid ring opening, which used acids and water to hydrolyze the epoxide ring and transform it into a 1,2 diol. The data would show an additional increase of 18 for each double bond since 2 hydrogen and 1 oxygen is added to the lipid. The final step was the periodate oxidation, which used the periodate ion to cleave the diols. The resulting data should show a decrease of mass depending on the location of the double bond. So for the actual procedure that I used, first of all, for the peroxy acid, I used metachloroperoxybenzoic acid, which is a suitable reagent because it is stable and it is in solid form at room temperature. So the first step, epoxidation, as you can see, I prepared a solution of MCPBA, the metachloroperoxybenzoic acid, at a concentration of 10,000 ppm by adding 0.1 grams of DMCPBA to 10 milliliters of 1:2 ratio of acetic acid to acetonitrile. Then I mixed 1 milliliter of the lipid standard, which for my first try, I used the PG 36 lipid, which has a double bond at the 9 position of one chain and another double bond at the 9 position of the other chain. So I mixed the lipid standard with equal amount of the MCPBA solution, and then I waited up to 10 minutes at room temperature undisturbed for the reaction to complete. After that, I analyzed it through the mass spectrometer, and these are the results. So I don't know if you can see here, but the initial lipid had a mass of 773. And after epoxidation of roughly 10 minutes, so this is at 5 minutes, which when it wasn't complete, you can see 773 as still the biggest, 789, 805, and then these are extraneous values. And then this is after 10 minutes when the reaction was fully complete. So you can see that the 773 is completely gone. The 789 is still there, but very small, and the 805 is dominant. So a value of 16 was added for each double bond, which indicates that there are 2 double bonds existing within this particular isomer. The next step, acid ring opening, I used sulfuric acid, mixed it with mixed in 3-to-1 ratio of acetonitrile to water at a concentration of 0.135 molar. So I added 1 milliliter of this, which is equal to what I used for the other two reagents so far. I added 1 milliliters of it to the solution, epoxide solution, and then I waited for around 30 minutes. So this is the data. I don't know if you can see clearly, but while the dials did form, so I can see a value of 807, 823, 841. All of them are dial data, which are good, but there were too many byproducts, which led me to omitting it in the end. But anyways, this was the results. And one thing to note that was this reaction was much slower than the epoxidation reaction. And if I did include it in the end, it would have taken much longer for the process to complete and potentially reduce the effectiveness of the quick, rapid testing idea of the project. Anyway, the last step, periodate oxidation, I used sodium periodate, which again was chosen because it is a relatively stable salt at room temperature. And I mixed 0.1 grams of it with 3-to-1 ratio of acetonitrile and water to create a 10,000 ppm solution of it. So I added 1 milliliter again of this periodic solution to the initially dial solution, and then later on I omitted that step and added it to the epoxide solution directly. So the first one here, I believe, is the periodate solution that was reacted with the dial. So figure 7 here. I did get the desired products, but there were too many byproducts, which further motivated me into omitting the acid reaction step. These two were reacted directly with the epoxide, and as you can see, it is much cleaner. There are many peaks, but they're all from the same product, so it's better. But I got the desired products, which was 553 plus minus 16 and 663 plus minus 16, which represents a cleavage of 2 and 1 of the fatty acid chains each. So since the chain had, the cleaved portion of the chain had 9 carbon rings, and each carbon on average would have 2 hydrogen, I made this formula, which would give you the expected mass of the lipid after the cleavage. So it would be the initial mass of the lipid minus 14 times the number of carbon plus minus 16. That will be your desired product. But anyways, in the end, I omitted the acid step, but kept the other two and decided to roll off it. Oh, and also the periodic reaction was relatively quicker than the acid reaction, and it was mostly complete within 30 minutes. Next, I used E. coli to analyze the effects of this reaction. So here we can see the initial lipid, initial E. coli standard data. So it shows many peaks, and this chart represents the expected lipid composition of E. coli. So again, I used the same procedures for epoxidation and the periodic reaction. So the epoxidation went successfully, although it was much slower than when done with a singular lipid, and it still showed these, for example, 773 to be slightly dominant. But it also showed the other two products, which was good. And it seems that 747 has also reacted, which, according to the chart, has 1 isomer that can have 1 double bond. So it added a mass of 16, and there were no further additions of 16, which meant that the reaction went well. Next, I did the periodic reaction. And this time the results were not as clean. So I did end up getting a clean and effective enough data to be able to analyze the lipid composition, but we can see that it's quite difficult to be able to accurately distinguish the lipids. So here I listed out the potential isomers that could have been these masses. And some of these data do appear on the lipid database. So it does indicate that the method does work. But regardless of that, the method overall nevertheless works, and it can be used as an alternative for conventional methods like PCR that take up to 3 days to be able to complete. And this, on the contrary, besides the bacteria culturing time, only takes at most 40 minutes, if done quickly. And as we can see, the lipid isomers were effectively distinguished whether this is clean, whether we can actually evaluate the identity of the lipid position isomers or not. But anyways, if by using this, it would be possible for even subspecies level of detection to be possible. So in conclusion, the method allows for evaluation of lipid composition of different bacteria, especially at subspecies level where the MZ data is practically indistinguishable. So by doing this, we can further differentiate the mass data of each bacteria and thus implement or develop a new method for bacteria detection. Now, some further research is needed for the actual accurate interpretation of each of these masses, because in order to accurately distinguish the bacteria without having to eyeball it, so-called, you would have to be able to figure out the real identity of these lipids and list them out so that the database could be created for the automation of the bacteria detection. And some experimental errors that may have happened include first of all, how pure each of these reagents and the lipid and E. coli standards were. As you can see, there are some background values that appear upon here, and even for here, I do not know what these peaks are. So that is one thing that we have to keep in mind when analyzing these data. And another issue that I saw is that some of the mass data here for the periodate on E. coli seem to have a decrease and addition of 2 in some cases. I don't know what that is, but further research would need to be done for the identification of these errors. But that concludes my project, and thank you very much for taking the time to listen to my presentation.